Hey, AP Chemsters, this is Mrs. Blankwalle bringing you the Chapter 4 blank walls. And if you recall Chapter 4, it is all about like stoichiometry, chemical quantities and aqueous reactions. And so stoichiometry is when you did the BCA tables from your previous year. First time you had chemistry, and we're going to go revisit that. We're going to talk about limiting reactants. We're going to talk about ionic and net ionic reactions, which probably will be new for most of you. So let's just begin and just talk about stoichiometry. So it says stoichiometry is probably the most important thing you can ever learn as you take AP Chemistry. Get really good at BCA tables. They do not go away. Ask any former AP Chemster. You will be doing BCA tables or things like BCA tables really for the rest of the year. It does not go away. Learn it now. If you didn't learn it the first time, learn it now. So what is stoichiometry? The word stoichiometry comes from Greek words, stoichion, that means element, and metron, which means to measure. You probably could figure that one out. Deals with the calculation about masses, maybe volumes of reactants and products involved in a chemical reaction. Okay, so how do we do this? Well, there are many different ways to do it. I prefer this thing called a BCA table, okay? You will see why probably later on why the BCA table is so handy, and especially in AP Chemistry. It's easy to use. You can easily answer questions that may be asked you, like which is the limiting reactant, how much excess do you have, how much of this did you make, but also it ties in very, very, very closely to a type of a table that we're going to use in equilibrium. So if you understand the BCA, you'll understand the equilibrium table, okay? So how do you begin? So what is the first thing you have to do? If it's not given to you, you have to make sure you write down the correct formula. This is why I keep giving you nomenclature quizzes. If you goof on your formulas, you're never going to get this thing right, okay? You won't be able to balance it, and your stoichiometry is going to be off, and it's just going to be a mess. So I still might throw in some more nomenclature quizzes at you, because you have to know the correct formula. You still have to know your polyatomic ions. You still have to know how to do a covalent, all right, things like that, okay? After that, if you have the correct formulas, then you need to balance your chemical reaction. So if you notice, if you wrote the formula down wrong, you may not be able to balance it. I know if I make a mistake on one of your handouts that I can't balance it if I made a typing error too. So make sure that you have your correct formula so then you can balance it, okay? And what do those coefficients mean? Those mean moles. So if you're reading a balanced equation, you might say 2 moles of methane plus 4 moles of oxygen reacts to produce, all right? So those coefficients mean moles, and that's really important, okay? So then you also probably will have to calculate your correct molar masses. And if you wrote your formulas down wrong, you're going to get the wrong molar masses, okay? So all that is like what you have to already know before we even start the BCA table, okay? So what does a BCA table even look like? Okay, so right here you have, one reactant plus another reactant. You may only have one reactant if it's a decomposition, but all right. Produces product number 1 and product number 2. Now, your B stands for before. See that? Before stands for before. So how much reactants are you given? Should be in the problem typically, okay? And consider this. How much product do you start with before you even start the reaction? You don't have any product. That's why these are zeros. All right, and then as a reaction goes, your reactants are going to be used up, so that's why we subtract here, and you're going to produce more products. That's why you're going to add here. So then this is your change. Your C stands for change. So what's happening throughout this reaction? And then A stands for after, and so you take your given minus X and you get an answer. Take your given minus Y, there's another answer. 0 plus A will be A, and 0 plus B is B. So real quick, what are X, Y, A, B's? These are called what? Mole ratios, okay? Derived from what? The balanced equation. If your equation isn't balanced, you're not gonna, your numbers aren't gonna be right. So this is huge right here. This is huge, huge, huge. All values must be in moles in a BCA table. If you're not given moles in the problem, typically you'll be given grams, then what? You have to convert to moles from your given grams, you're given liters, you're given molecules, and that's what goes in the given category. Okay, so all these things here must be in moles to do a BCA table. Okay, so let's check this next one out. Let's look at problem number 1. Okay, it says under certain conditions, sodium can react with oxygen to form sodium oxide according to the unbalanced reaction below. Draw a molecular representation of this reaction if the given amount of oxygen is present. All right, so let's check this out. What's the first thing we have to do? Write down correct formulas. Well, Mrs. Vanderwille already did that for you. So what's the second thing we need to do? We need to, yes, balance it. Go ahead, pause this, balance it. All right, how'd you do? So hopefully you are looking at this as well. These are both elements, so it makes a difference what I start with. So if I have 1 sodium, I have 2 sodiums, I could put a 2 here. But hang on, I have 2 oxygens and 1 oxygen. So really, what should I do here? I should put a 2 here. Now what changes is the amount of sodium, okay? So I'll have that there. If you would like to, oops, you can put a 1 here, but you don't have to. So obviously I have a given amount of oxygen. Well, let me go ahead and bring those up here. So I just use these here. And what happened? They did not tell you anything about your sodium, all right? So we can call this excess, all right? You have plenty of sodium because they didn't tell you anything about it. So what did I do? I just took a whole bunch of them and put them right there, okay? So I probably won't use all of these up, but I have lots of them there. So now what do we do? Well, I'm going to start making some sodium oxide. So to make sodium oxide, I need 2 sodiums and 1 oxygen, all right? So now I'm going to use 2 sodiums and 1 oxygen, all right? And I'm going to keep doing this until something runs out, all right? Well, I'm going to use some of these over here. So let me use 2 sodiums and 1 oxygen, all right? Oops. And then I'm going to take 2 more sodiums and 1 more oxygen. I'm not done yet. I still have leftovers of both things. I'm going to take 2 sodiums and I'm going to take 1 oxygen. Isn't this exciting? And now I'm going to take 2 sodiums and I'm going to make 1 oxygen. Well, here we go. I ran out of my oxygens. And does that make sense? Hopefully so, because what did I say about my sodium? It's excess. I have lots of it. I have plenty of it. So I've leftover sodiums as well, okay? But what happened to all my oxygens? They're gone, okay? So look here what happened, okay? Notice I started out with 3 molecules of oxygen, right? Isn't that what it says here? If the given amount is present, I have 3 molecules. So in my 3 molecules, I used them all up, so 3 molecules are gone. How many molecules of sodium oxide did I make? I made 6. Isn't 6 twice the amount of 3? Yes. Why is that? Is that a fluke? No. Look at this. This is a 1. This is a 2. This is my mole ratio. So my recipe says for every 1 mole of oxygen, I'll make 2 moles of sodium oxide. Well, what if I start off with more than 1 mole of oxygen, like 3 moles of oxygen? What do I make? Twice as much. Okay, I make 6. So how could I finish out my thing here? So how many sodiums did I end up using up? Well, it looks like I used up, what? 12 of them, didn't I? All right. So I have 12 of them used up. How many of my oxygens did I use up? I used up 3 of them, right? 3 molecules. And how many of these did I make? It looks like I made 6. Now, do those numbers make sense to you? Hopefully so, because look at this mole ratio. This is 4 times bigger than this. This is 4 times bigger than this. That's the idea of the mole ratio. And then what is going on here? A stands for after. So I have leftovers. Now they, again, didn't tell me how much I actually started with, but I still have excess sodium here. So don't worry about the fact there's 6 of them. I just threw some sodiums out there, so I know I have leftovers. So subtract what's lots minus 12. I still have leftovers. But what's 3 minus 3? Isn't that 0? And that tells me that's my limiting reactant. It got all used up. And then how many did I start with here? I had none to start with. It was a blank slate. So now what I do, I'm going to add, because I'm producing my products, and I get 6. Okay. So that would be the molecular representation if I have 3 molecules, or in this case 3 moles of oxygen present. So real quick, I want to show you something before we go on. How can I do this without drawing pictures? How do I know these numbers if I'm not moving around little circles, all right? Well, start off with what you have. This is a 3. Drop it down. So put your 3 here. So now divide by what you have, multiply by what you want. So it's 3 divided by 1, 3. 3 times 2 is 6, correct. Let's try it again. What's 3 divided by 1? 3. 3 times 4 is 12. That's how you come up with those numbers. So again, divide by what you have. So if I start off having oxygen, I'll divide it by its coefficient 1, and then multiply by what you want. Multiply the coefficient by 2, or multiply it by the coefficient of 4. And so we'll be practicing this, don't worry. Okay, let's go on to the next page. So this section is actually talking about that mole ratio. So how do you solve for that C part of the BCA table, the change, okay? So the problem states that there's actually 22.0 moles of octane. Then how many moles of oxygen are you going to use? How many moles of carbon dioxide will you produce? How many moles of water will you produce? So start with what you have, 22, divide it by its coefficient. See, oh, look at that, factor labeling. You're going to put this in the denominator so that the units are going to cancel out. Oops, sorry. So it is in the denominator, all right? And then multiply by what you want. That's your numerator, isn't it? So take your 22, divide it by the coefficient of what you have, multiply it by the coefficient of what you want. Yes, I'm showing you my little shortcut works by factor labeling. Okay, try it again. Here's what I have, divide by what I have. Hey, that's my coefficient, isn't it? So if I start off with it, divide by the 2, so they cancel each other out, right? Multiply by what you want, moles of carbon dioxide, and voila, that's how many moles of carbon dioxide you get. Same thing here. Here's what I have, moles of octane. Divide it by what you have, which is the by what you have, the moles of octane. Stop it. And then multiply by what you want. Okay, so the moles of octane cancel out. So you take 22 divided by 2, multiply it by the 18. Okay, so what's going to happen here? This is what your BCA table will look like. What do I have first? 22. Remember what I did with factor labeling? So bring it down, what you have. So 22 divided by 2, why? Because it's in the denominator to cancel them out, times by what you want, 25 times 16, or times by 18. And that's where these numbers come from. You subtract your reactants, you add your products. So 22 minus 22 is 0. What does that tell me? I don't have any octane left over. It's all used up. If I have lots and lots and lots of oxygen, I take out 275, I still have plenty left over, like I did with the sodium on the prior page. Here I have carbon dioxide. I'm going to produce carbon dioxide, so you add it. I'm going to produce water, so I'm going to add it. Okay, I'm going to stop here, and the next one we'll pick up on problem number 2. So, as you know, I always end with, don't wait to be great. Bye, see you next time.